Hi everyone, my name is Sadi Afroz. I'm going to talk about censorship circumvention. This is a joint work with Michael Shantz from IEEE and Vern Paxton from IEEE and UC Berkeley and an anonymous author. The goal of this paper is to understand the real-world censorship problems we face today and how research in censorship circumvention address them. So we start by looking at how censors do censorship in the real world, and then relate that threat model with the threat models of the circumvention systems that we see in the research. We found that the circumvention tools that are deployed in the real world, their threat model aligns with the sensors that we see in the real world, but the research in the censorship circumvention systems focus on sensors that do not exist today. So we look at censorship circumvention in the real world. So let's give you an example of the censorship scenario we consider. Let's suppose you have a user in some censored country, for example, China, that wants to access some website that is censored in that country. For example, if a Chinese user wants to go to a Wikipedia page that is blocked in China. So what did that user do? She can download a circumvention systems like Tor and then install it and then use Tor to bypass the censor. But censors like China already knows that people are doing it. So now most of the Tor relays are blocked in China. Now if the user wants to use Tor in China, they have to obfuscate their traffic to Tor. So this is the current censorship scenario I'm going to talk about. That I'm going to focus on nation-state censorship that prevents people from accessing web resources outside the censor's jurisdiction. I'm going to focus on only the kind of censorship circumvention systems that allow users to do that. That is, the channel-based circumvention systems that help user bypass a nation-state censor and allow user to communicate with resources outside the censor's jurisdiction and enable low latency connections, roughly fast enough for web browsing. Even this limited scope is a pretty large space. We studied 55 censorship circumvention papers. 33 of them were academic papers. 25 of them are already deployed in the real world. We also looked at 4 papers that analyzes other censorship circumvention systems and evaluate them. To understand how censors behave in the real world, we studied 31 censorship measurement papers. We also explored thousands of bug reports and blog posts from Tor. So let's first look at what do we know about the censors. In the 31 measurement papers we studied, we noticed 4 different characteristics of censors. A censor could be an in-path censor or an on-path censor. An example of an in-path censor is Blue Code. Syria and Qatar was using Blue Code to do censorship. An in-path censor has some capabilities, like it can drop packets, but it also has some limitations in terms of the processing power, because whatever it wants to do, it has to do it at the line speed. On the other hand, the Great Firewall of China is an on-path sensor. It's a passive sensor that can monitor any traffic that is passing by. And this sensor also has some capabilities and limitations. The capabilities is that it can do much more intensive processing, but the limitations are that it cannot drop packets. It can only inject packets. So there are some attacks in the research that are proposed that allows dropping packets. Those kind of attacks is not going to work in China. A sensor could be a stateless sensor or a stateful sensors. A stateless sensor cannot do packet reassembly. For example, before 2007, the Chinese sensor was a stateless sensor. So if a packet is getting blocked, you can just break the packet into 2 and then transmit it, and that would just bypass the sensor. But this attack would not work now, because now the sensor is stateful and it can do packet reassembly. Majority of the sensors we studied, we found they use blacklist-based sensors. We found only 2 cases where the sensor is whitelist. It was Iran during their election in 2013. They disallowed all non-HTTP traffic. The last characteristic of the sensor that we found is interesting is the censorship timeline. When do sensors do censorship? Every censor has some motivation for doing censorship. For example, China and Iran do censorship to reduce political unrest. So usually censorship happens during or before some political event. This is important for tool developers or activists to understand, because if you know when censorship is going to happen, you can prepare beforehand for situations like this. In all of these measurement papers, we found only 4 papers that looks at censorship of the circumvention tools. 3 of these papers focus on how China blocks Tor. 1 paper looks at the leaked logs of a blue code device that was deployed in Syria in 2011 and found that Syria was using blue code to block Tor. So now we need to have a better understanding of how censors block circumvention tools. We noticed that every time Tor is blocked in some countries, people would either report a bug report on the Tor bug thread or post a comment on the Tor blog. So we downloaded thousands of Tor bug reports and blog posts and used a machine learning approach to identify such reports, to identify events when Tor was blocked by some countries. This graph shows the Tor blocking events that we found. We found 34 Tor blocking incidents. Majority of this happened in Iran and China, along with 9 other countries that blocked Tor once or twice. We found 4 main categories of attacks that censors use to block Tor. Majority of them uses just an IP address block list. The other attack that we notice is a censor using properties of a protocol to block Tor. These properties could be what kind of cipher suite Tor uses, or the certificate timeline of an SSL certificate. Some censors look at the pattern in the web request to block Tor. We found only 2 cases of advanced blocking, which is called active probing. Here, the censor actively sends a request to the Tor node, and if the Tor node responds back, then they block the node. Now that we know how censors block circumvention tools, let's look at the research in censorship circumvention and try to understand how well these censorship circumvention systems help us against the real censors. We categorized all the censorship circumvention tools in 2 dimensions. What kind of properties they hide and what kind of techniques they use to hide this. The properties we looked at is, the properties the systems looked at are either properties of the setup, the connection setup, or properties of the connection usage. The techniques the system use are divided into 2 categories. There are either polymorphic system. Polymorphism is hiding a traffic to make it look random. Or they could be steganographic system. Steganography means hiding a system to make it look like something else. An example of a polymorphic system would be Tor's ops proxy that creates an encryption layer on top of Tor traffic to make it look like a random traffic. An example of a steganographic system would be Skype morph, which makes Tor traffic look like Skype. Now, let's look at this table again. All the tools in the blue font are the tools that are deployed in the real world. Those tools already have users. All the tools in the black font are the tools that are proposed by research that are not deployed. Do you notice any pattern? So we see here that most of the real world tools focus on hiding the properties of the setup, and they do polymorphism kind of technique to achieve that. Most of the tools proposed in research focus on patterns of the usage, for example, pattern of packet length distributions, and they usually do some kind of steganographic systems to achieve that. So then we wanted to look at how do the systems evaluate themselves to understand how well their tool will work in practice. So for that, we looked at the evaluation criteria these systems use to evaluate themselves. In the 55 papers, we found 74 metrics that these tools use to evaluate themselves. Now, I want to clarify here that we are not comparing 2 systems based on how well they do in one specific criteria. For example, I'm not going to say that tool A is faster than tool B. We just look at whether tool A and tool B both checked the speed of a connection while they were evaluating their system. So this is an evaluation of the tools. One thing is very evident from this graph is that this is a very, very sparse table. This is because different systems use different criteria to evaluate themselves, which is understandable because different techniques are, some techniques are so different from one another that you need different ways to evaluate it. But it is problematic for a user or activist perspective because it does not answer the question that how well a specific system will work in a specific censorship context. So we propose that evaluation of a circumvention systems should be from the user's perspective rather than from the technique's perspective. So it should focus on the need and the censorship context of the user rather than specific techniques that is the system is proposing. We also notice that we don't have any holistic metric for evaluating undeployed approaches. For example, if you want to know how well a deployed approach works, you can look at how many users it has, or has it been blocked in many other countries with censors. But we don't have any such criteria for tools that are not deployed yet. We also noticed that real-world tools focus a lot on the cost of maintaining the tool and the usability of the tool, but very few research papers mention these two criteria. So now we focus our attention to the papers that attack proposed circumvention systems to see how well the systems can be blocked by the real-world censors. Here again, we contrast these attacks we found in research papers with the attacks we saw in the real world. Here in this graph, the red bars are the attacks that we saw in the papers, and the blue are the attacks we saw in the real world. We looked at several properties of the attacks. The first property we looked at that at which phase of the connection the attack happens. The attack can happen when the user is collecting identifiers. The attack can happen during setting up a system, or it can happen while using the system. It can also happen when a censor is in its spare time connecting to a server to see what kind of response it gives, and that is the attack we call subsidiary attack. And from this graph, you can see real-world censors mostly focus on attacks of the identifier management or the link setup, whereas research censors mostly look at the attacks of the channel usage. The next thing we looked at is the activeness of a censor, how actively a censor has to be involved in an attack to perform it. A censor could be a passive sensor that passively monitors every traffic. It could be a proactive sensor that sends some traffic to some node and wait for a response. It could be a reactive sensor that is similar to a proactive sensor, but instead of sending its own traffic, it modifies the traffic of the user. And here again, you see that real-world sensors are usually mostly passive, or it could be sometimes proactive, but we notice reactive sensors that research papers considered. The last thing we have looked at is the robustness of an attack to packet loss. Packet loss in a network is very common. So what happens if the packet that the sensor was using to decide whether to block a flow is lost? We notice a real-world sensor in the packet loss case is going to underblock, whereas a sensor that we found in research papers is going to overblock. For example, if a real-world sensor is looking at the Tor IP address in a packet and the packet with the Tor IP address is lost, it's just not going to block that flow. But if you have an attack that looks for an absence of a response and the response is lost because of packet loss, the sensor is going to block it. And this is the kind of sensor that research papers consider. So in summary, we did an extensive study of censorship measurement in the real world and censorship measurement we see in research papers. We collected a lot of data from different sources, and we noticed that the censorship problems that we see in the research is very different from the censorship problems real-world users face today. So one of the agenda of this paper is to realign some of the research effort to solve the real-world censorship problems. Now, if we want to talk about what makes a censorship system successful, we need to define what do we mean by success. Different systems and different different use cases are going to vary. So we cannot have just one fixed list of criteria that we want all systems to follow, but we can come up with some abstract criteria that can be a guide to all these circumvention systems. One such criteria could be good put and cost. That is, how much productive evading traffic your system provide and at what cost. This metric is flexible because you can define what do you mean by good put, what do you mean by cost. But it's also concrete because it has a specific meaning. We have very limited ideas about the censorship mechanism and what kind of a technical measurement a sensor is allowed to do. For example, we still don't know how long does it take for a sensor to block a system. Many people have suggested that one way to get ahead of the censorship arms race is to deploy low-cost circumvention tools one after the other so that the sensor will not have enough time to block all of them. But we don't know whether this kind of system will work because we don't know what technical measurement sensors are allowed to do. And that brings me to my last point, is an evading engine. Censorship circumvention system is still very reactive. We come up with an idea, we implement it, and we deploy it, and then wait for the sensors to block it. And in many cases, we find that in spite of all this complicated crypto we put in our system, the sensor is looking at the certificate lifetime to block the tool. So it would be very useful to have an automated evaluation engine for the developers to identify these simple techniques that the sensor are probably going to use to block your system. All the data we collected for this study is openly available in our website, internetfreedomscience.org. And that was my talk. Thanks a lot.